Hello and welcome to IP lesson. In this lesson, we will learn about STP and RSTP. So STP and RSTP are very similar. Most of what we discussed in the previous lesson works for both for STP and RSTP. So STP and RSTP locking one port in order to prevent the loop in our environment in case of redundant link. So both STP and RSTP will start to block the ports from forwarding any frame, and it will only forward the PBDU message, Bridge Protocol Data Unit message. Inside that message, it will have something called Bridge ID and information about the interfaces. After that, our switches will do election in order to choose the root bridge switch. The root bridge switch will be the switch with the lowest bridge ID. After spanning tree protocol, choose a root bridge switch. The root bridge switch interfaces will be designated forward, and the root cost of that interfaces will be 0. Next step, all the switches will calculate the path cost in order to reach the root bridge switch. So the path cost will be the total root cost from the switch to our root bridge, and the root cost assigned by the spanning tree protocol. The interfaces with the lowest path cost will be a root port. The second interface will be designated port, and the designated port is a port with higher path cost than the root port. So all the switches will do the same thing until we find the longest path, and the longest path interface will be the blocked port. So this mechanism works for both STP and RSTP. So the STP protocol, or the regular STP protocol, is a very old protocol. It's created by the IEEE. The standard name is 802.1d. The STP protocol cannot be configured on Cisco devices, and the Cisco replaces the STP with a protocol called BVST+. There is also the RSTP, Rapid Spanning Tree Protocol. This is IEEE. This is a standard protocol. The standard name is 802.1w. RSTP cannot be configured on Cisco devices, and the Cisco replaces that protocol with RBVST+. Rapid Bare VLAN Spanning Tree Protocol Plus. So BVST Plus is a Cisco proprietary protocol, which means this protocol cannot be configured in any other devices than Cisco. BVST Plus is a default spanning tree protocol that works on Cisco devices. So by default, when we purchase Cisco switch, it will have the BVST Plus enabled by default. We have also the RBVST Plus, and this is a Cisco proprietary protocol, and we can configure that protocol on Cisco devices. We have also MSTP, Multiple Spanning Tree Protocol. This is a standard protocol created by IEEE. The standard name is 802.1s, and this is the only standard protocol that we can configure in Cisco devices. Cisco adapt MSTP protocol and didn't do any changes to the standard protocol. So let's ask a question here. Why Cisco didn't adapt the STP and the RSTP protocol? So Cisco actually did a great job on the spanning tree protocol, and the reason of not adopting the STP and the RSTP is that both of those protocols are CST. CST mean Common Spanning Tree Protocol. Let's take a look at our example to understand what is CST. In our example, we have switch 1, switch 2, and switch 3. So for Common Spanning Tree Protocol, there is only one spanning tree will work for all the VLANs. In our example, Spanning Tree Protocol blocked the port G1 on switch 3. So G1 will be the blocked port for VLAN 1, VLAN 2, VLAN 3, and any VLAN configured in our devices. For BVST Plus and RBVST Plus, it doesn't do one calculation in order to block the port. The blocking will be based on the VLANs. For example, for VLAN 1, we can plug the interface G1 on switch 3. Switch 2 is our root bridge, and for VLAN 3, we can change the root bridge to become switch 1, and in that case, we will block interface G1 on switch 2. If we have another VLAN, we can also change the configuration and choose any switch to become the root bridge. So right now for Cisco devices, in order to configure the spanning tree, we have to put spanning tree command, and after that command, we have to specify the VLAN that we need to change the spanning tree for. So let's take a look at some differences between the STP and the RSTP. We spoke before about the max edge time, and the max edge time is the time that will take in order to consider a topology change. The max edge time in the classic spanning tree was 20 seconds or 10 hellos. So if we didn't hear from our neighbor 10 hellos, we will consider that there is a topology change in our network. For rapid spanning tree protocol, we can modify this time and make it 6 seconds or 3 hellos. If we didn't receive 3 hellos from our neighbor, we will consider that a topology change in our network. Another big difference between the STP and the RSTP is that RSTP are using a keep alive mechanism. So instead of our switch wait until the max edge time pass in order to identify a topology change in our network, our switches will use the keep alive mechanism. And we can simply think of the keep alive mechanism that our switches will keep sending a message, and this message is just checking if the network is stable or not. Next we have the RSTP port rules. So for STP and RSTP, they both have the root port, the designated port, and the disabled port. So the new port rule is the alternate port, and the alternate port is a port to replace a root port if root port fail. We have also the backup port. So the backup port is a port to replace designated port if the designated port fail. Please keep in mind that the backup port used only if we have one device in one collision domain, and the only device that can be one collision domain is the hub. So the big differences between STP and RSTP is the alternate port. Alternate port will be the blocked port in RSTP, and however this port is in a blocking state, it will receive PBDU message and it will send PBDU message also. Also the alternate port will accept inferior PBDU message in case of topology change. So as you can see, switch 3 can only reach the root bridge through interface G1, and interface G2 is alternate blocking. So if switch 3 lost the connection to switch 1, it will not be able to communicate to the root bridge. In that case, it can accept inferior PBDU message through switch 2. So switch 2 can send him a PBDU message telling him that he is a root bridge. This is just to happen if switch 3 lost the connection to the root bridge. The next new port rule in RSTP is the backup port. Backup port work only with a device in the same collision domain, which is hub. So hub create one collision domain in our network. We don't have to worry about collision domain, but the backup port can replace the designated port in case if we have a hub in our network. So when we are using a hub in our network, similar to our topology here, we have hub 1. Hub 1 have a redundant link. In that case, one port will be designated port and the other port will be backup port. In case of the designated port fail, the backup port can take over without any delay. Let's take a look at the STP convergence, and we mean by convergence here that if something happened to our network, for example, a link goes down, in that case, STP will do two things. It will do flushing to the MAC address table, and it will send TC or topology change message. Some people also call it TCN, which stands for topology change notification. What we will discuss here works the same for STP and RSTP protocol. So here in our topology, we have three switches, switch 1, switch 2, and switch 3. Switch 3 interface, G2 is the alternate blocking port. And in our example, the link between switch 1 and switch 2 goes down. Let's see how spanning tree will handle this. So let's add two PCs also in order to understand what is the flushing that will happen for the MAC address table. So we have PC1 with MAC address all A and PC2 with MAC address all B. By default, the MAC address table will have an aging time 300 seconds or 5 minutes, and this is the time for how long our MAC address table will keep a MAC address. So if we learn a MAC address, we will keep it on the MAC address table for 5 minutes, and after that time, the MAC address table will delete this MAC address and start the learning process again. So this time is acceptable for a stable network, but imagine that we have to wait those 5 minutes in order to remove learned MAC address in case if we have a failure, if we have a link goes down. So flushing MAC address means deleting all the MAC addresses. So as we can see, switch 2 will delete PC2 MAC address and all the MAC addresses from the MAC address table, and also it will reduce the aging time to 15 seconds instead of 300 seconds. After that, all the switches will send TC message, topology change notification message, and the topology change notification message will tell the switches to do two things. First thing, it will tell the switches to reduce the aging time to 15 seconds. And also it will tell the switches to flush the MAC address table except the one where it receives the topology change notification on. So in our case, when switch 2 send the topology change notification, switch 3 will delete all the MAC addresses that he learned except interface G2 MAC address because it received the topology change from that interface. The next big difference between STP and RSTP is sending the PBDU hello message. For classic spanning tree protocol, the hello PBDU message sent to the root bridge. For RSTP, the hello message are exchanged between all the switches. Same thing for the TCN or topology change notification. For classic spanning tree protocol, the TCN sent with the destination of the root bridge switch, and for the RSTP, the TCN exchanged between all the switches. For RSTP, we have a new port types. The first type is the point-to-point port, and the point-to-point port is the link between two switches, as we can see in our topology. Next we have the point-to-point edge port, which is the link between switches and end devices. After that, we have the shared port, and the shared port is the link between switch and the hub. For classic spanning tree and RSTP, there is something called port fast. So for classic spanning tree, it called port fast. For rapid spanning tree protocol, it called edge port. And port fast is a feature that allow ports connected to end devices to be in forwarding state immediately instead of go through discarding learning forwarding or blocking listen learning forwarding. So in our topology, we have an end device that is connected to switch. Right now, I'm talking about the end device that is connected to the switch on the right side. So this port is not configured with port fast command. In that case, this port will go in discarding, learning, and then forwarding. So think about this. Is this port have a redundant link? Will that port affect in our topology for STP perspective? Is that port can exchange PBDU message? Will that interface become a root bridge to our network? And the answer is no for all of that. For that reason, we can configure our interface with port fast command. This is only for the ports that is connected to the end devices. And in that case, it will skip the discarding and learning process, and it will go to the forwarding right away. In order to secure our devices, we can use a command called PBDU Gaurd. So the PBDU Gaurd command will prevent the switch from accepting any PBDU message on the configured interface. So in our topology, we have 3 switches and 1 end devices connected to one of our switches. So a hacker can be connected to that interface and can send a superior PBDU message. In that case, the hacker device will be the root bridge for our network, and it can receive the hello PBDU message, which include bridge ID of the switches and information about interfaces. So this is a vulnerability to our network. And in that case, we can configure the interfaces that is connected to end devices with the command PBDU Gaurd. If the hacker try to send a superior PBDU message, our switch will disable this interface. And this is how can we secure our switches from receiving PBDU messages in the interfaces that is connected to end devices. This is the end for this video. Thank you for watching and see you in the next one.